enginerdmath channel. We're live. Our topic for today is inverse hyperbolic functions of complex numbers, which is part 2. So I already have part 1 for this topic, inverse hyperbolic functions of complex numbers. I will just put the link in the description if you haven't watched yet. Also, aside from that, I already have previous videos all about complex numbers like operations on complex numbers such as addition, multiplication, subtraction, division of complex numbers in rectangular forms, simplifying powers of imaginary number I, converting or transforming complex numbers in rectangular form to polar form or exponential form or vice versa, operations of complex numbers in rectangular, polar, and exponential forms, powers and roots of complex numbers, exponential functions of complex number with the base e, natural logarithm of complex numbers, logarithm of complex number to another complex number base, complex number raised to complex number, trigonometric functions of complex number, inverse trigonometric functions of complex number, and hyperbolic functions of complex number. So if you haven't watched that yet, I will just put the links on the description so you can check them first because it is important you have watched them already before proceeding with the current topic because everything that we've learned there will be applied here. So we will just continue solving problems all about this topic, inverse hyperbolic functions of complex number, because on part 1, we have just solved 3 problems, particularly arcsinc for arcsinc C, arccos Z, and arctanc Z. So we will continue. We will try to solve examples on evaluating inverse hyperbolic functions of complex numbers such as arccosec C, arcsec Z, and arccoth Z. Okay? So here are the formula that we will use. So you need to memorize them again. Arcsinc Z is equal to ln of Z plus square root of 1 plus Z square. Arccos Z is equal to ln Z plus square root of Z squared minus 1. Arctan Z is equal to 1 half ln of 1 plus Z over 1 minus Z. Arccosec Z is equal to ln 1 plus square root of Z squared plus 1 over Z. Arcsec Z is equal to ln of 1 plus square root of 1 minus Z squared over Z. And arccoth Z is equal to 1 half ln of Z plus 1 over Z minus 1. So here are the past examples that we have solved in part 1. Not this one. These are all the problems that we have solved in the past live streams. Okay. So here are the problems that we solved in part 1. Arcsinc of 2 plus 3i. Arccos of negative 7 plus 5i. And arctanc of 5 minus 8i. So let's continue. Let's have problem number 4. Okay, evaluate this complex number arccosec of 2 plus 7i. So what's the formula for arccosec Z? Looking back at the list of formula, we have arccosec C is equal to ln of 1 plus square root of Z squared plus 1 over Z. Okay, arccosec Z is equal to ln of 1 plus square root of Z squared minus 1 over Z. wherein the value of z is 2 plus 7i. So substituting the value, we have arc cosec of z, which is 2 plus 7i, is equal to ln of 1 plus the square root of z, 2 plus 7i, quantity squared, minus 1 over z, 2 plus 7i. So we simplify first the expression inside the square root. We will have ln of 1 plus the square root, so square of binomial. Apply the special product shortcut formula. So square the first two. 2 squared, that's 4. Then plus the product of the first and the second. 2 times 7i, 14i. But we need to multiply by 2. So 2 times 14i, 28i. Okay, and then the square of second term, 7i. So 7i quantity square, that's 49i square minus 1 over 2 plus 7i. Simplifying further, we'll have ln of 1 plus the square root. So you can combine 4 minus 1, that's 5, plus 28i plus 49. I square is equal to negative 1, so that it's positive 49 times negative 1, or negative 49. Then over 2 plus 7i. So we have ln of 1 plus the square root. So combine 5 minus 49, negative 44, plus 28i divided by 2 plus 7i. So next, we will evaluate this square root of negative 44 plus 28i. So we will apply what we've learned from my previous video. The title is Powers and Roots of Complex Number. I will just put the link on the description. We will apply there the de Moivre's theorem. So we will convert first this negative 44 plus 48i. It is in rectangular form. Let's convert this first to polar form. So identify the x, the real part, it's negative 44. Identify the y, the coefficient of the imaginary part, positive 28. So in what quadrant does the complex number lie? We have negative x and positive y. Therefore, in quadrant 2. So what's the formula for r? Square root of x squared plus y squared. So square root of x, substitute the value, negative 44 squared plus y, 28 squared. And use your calculator. Okay, square root of negative 44 squared plus 28 squared, it's equal to 4 square root of 170. How about the formula for theta? So if the complex number is in quadrant 2, formula for theta is arctan y over x plus pi, right? Okay, and then substitute the values. Arctan of y, we have 28 over x, we have negative 44 plus pi. So using your calculator again, arctan of 28 over negative 44 plus pi. So it is approximately equal to 2.575 rad in 3 decimal place. You can also check directly Using your calculator, you can convert directly this negative 44 plus 28i complex number in rectangular form to polar. But make sure the mode of your calculator is in complex. So if mine is already in complex mode, in case not yet, you just press mode and then select 2 for complex. And make sure also that the mode of angle in your calculator is in radian. Mine is already in radian. In case it's not yet in radian for your calculator, just press shift, set up, and then input or press 4. Okay, so how do you convert this rectangular form of complex number to polar form using your calculator? So just input negative 44 plus 28i, negative 44 plus 28, and then the I is here, equal, then press shift 2, then 3 for our angle theta form or the polar form, then equal. So you will see that we got the same R modulus 4 square root of 170. Then same theta argument, approximately 2.575. Okay, now that we have converted to polar form, we can now apply the de Moivre's theorem formula. We have, therefore, the square root of negative 44 plus 28i is now equal to the square root of R, which is 4 square root of 170. Then angle of the theta, 2.575 plus 2 pi k over n. So the n here is the index. If it's a square root, the invisible index is 2, right? So you have over n, which is 2. And this will run for values of k here, 0 and 1. So that you will have two values. So that's why the arc coset has two sets of values because of the two square roots that we will get. Okay? So we will start with k equal to 0. So if k is equal to 0, therefore the square root of negative 4 plus 28i is equal. So copy square root of 4 times square root of 170. Then angle 2.575 plus 2 pi k. You set that to 0, substitute, over 2. Or basically, you can just remove this 2 pi times 0 because it's just 0. So you'll need to divide 2.575 by 2. 2.575 over 2. It is equal to 1.2875. 1.2875. It is also equal in polar trigonometric form to the square root of 4 square root of 170 cosine of 1.2875 plus I sine 1.2875. You can input this in your calculator in complex mode, or the easier way to convert this into rectangular is to just input the R angle theta form. So input square root of 4 square root of 170 angle of, not fraction, it's 1.2875. And we will get approximately 2.019, 3 decimal place, plus 6.934i. Okay. So this is the principal square root when we set k equal to 0. Now, we will substitute this value of square root here in the last simplified form of the formula. Let's copy. So this is the value of our coset of 2 plus 7i, right? So we will now substitute the square root here, this one. So ln of 1 plus, so this is square root, we have 2.019 plus 6.934i divided by 2 plus 7i. So you can simplify further this expression inside the ln. On the numerator first, you can combine the real parts. 1 plus 2.019, that will be 3.019, plus 6.934i divided by 2 plus 7i. So you need to divide complex numbers. They are both in rectangular form. So you can solve it manually, apply what we've learned on my previous video on division of complex numbers in rectangular form, but it's harder to solve this manually, divide this manually, because there are decimal places in the numerator. So I would prefer to use calculator, although you can solve it manually, okay? So let's just use our calculator. Let's input 3.019 plus 6.934i over 2 plus 7i. So we will get approximately in decimal ln of 1.3 decimal place. So this will become 0.30 already, right? Then minus 0.137i. So it's an exercise for you to check when you divide it manually that the answer will be this one. Okay. Now, we will evaluate the ln of this complex number. So how do we evaluate the ln of complex number? You can watch my video titled ln or natural logarithm of complex number. It is just linked on the description. But we will recall this. We will recall the formula for evaluating this ln of complex number. So how? Convert this complex number in rectangular form to polar form. So identify x, the real part is 1.030. Y, imaginary part is negative 0.137. So what quadrant? You have positive x and negative y. Therefore, you have complex number in quadrant 4. Okay? Then, same formula for r, square root of x squared plus y squared. Square root of x, that's 1.030 square, plus y, that's negative 0.137 quantity square. You can use your calculator. Square root of 1.030 square plus negative. Okay, negative 0.137 square. This is approximately equal to 1.039. For theta, if the complex number is in quadrant 4, the formula for theta is arctan y over x, right? So substitute the value for y, we have negative 0.137, over x, we have 1.030. Again, input that in your calculator. Arctan of negative 0.137 divided by 1.030, it's approximately negative 0.132 rad. Okay, again, you can convert this directly to polar form using your calculator. Just input this complex number in rectangular form, 1.030 minus, excuse me, 0.137i equal. Then press shift to 3 equal. So you will see we got the same r modulus, approximately 1.039. And then the same argument theta, approximately negative 0.132. So the same. Next, let's now apply the formula in evaluating ln of complex number. So this ln of complex number, let's copy first. Applying the formula is now equivalent to what? The formula for ln z is ln of the modulus r plus I theta. Okay, if you recall. So substituting the value of r, 1.039 plus I theta, we have negative 0.132. ln of 1.039 is approximately equal to 0.038. Then this will be now minus 0.132i. Okay, so this is the principal value of the ln. Remember, ln is a multi-valued function. You can have infinitely many values, but this one is the principal value or PV. Okay. Having said that, ln has multiple values. We can have also its general value. So the general value for this ln is, so just copy the real part 0.038 plus copy the same theta negative 0.132, but you must always add multiple of 2 pi, or you add 2 pi n then I. So this is the general value, or for short GV, for all integers n. So that n can have values like 0, plus minus 1, plus minus 2, and so on. So by the way, this is already the answer. Also for the problem, arc cosec, right? The given arc cosec of 2 plus 7i. So arc cosec therefore is a multivalued function because of the inclusion of ln in its formula, which is a multivalued. So this is the principal value likewise of the cosec, arc cosec. Okay? And this is already the final answer. And this is the general value of the arc cosec. So this is the first set of answers. Like what I've said, we will have two sets of answers. This one is when we consider k is equal to 0. The next one is when we consider k is equal to 1. So we will still apply the same formula for the square root here. For the square root of this complex number, let's copy. But this time, we will set k equal to 1. So if k is equal to 1, therefore the square root of negative 4 plus 28i is square root of 4 square root of 170 angle 2.575 plus 2 pi k you set to 1. So you have 2 pi times 1 over 2. So we will have the square root of 4 square root of 170 angle. Then you can input this in your calculator. That's 575 plus 2 pi times 1, or simply 2 pi over 2. And you will get approximately 4.429. So in polar trigonometric form, it is equal to square root of 4 square root of 170 cosine of this theta 4.429 plus I sine 4.429. In rectangular form, again, you can just input this R angle theta form in your calculator. Square root of 4, square root of 170. Then angle of 4.429, which is approximately negative 2.019 in 3 decimal place, minus 6.934i. Okay. So we must plug in this value of the second square root in the original formula, which is this one. Okay, let's copy. So arc cosec of 2 plus 7i is now approximately equal to ln of 1 plus this square root of negative 44 plus 20i. The second value that we got is this one. So we will have negative 2.019 minus 6.934i. then over 2 plus 7i. Okay? So you can still combine the real parts here. 1 plus negative 2.019. So that's just ln of negative 1.019, right? Then copy this imaginary part minus 6.934i divided by 2 plus 7i. Again, you can divide this manually, but due to the presence of decimal points or decimal place values here, we will just use our calculator to simplify this division. So, input negative 1.019 minus 6.9393 sorry 934 9 6 point there's no 9 6.934i over 2 plus 7i, and it is approximately equal to, in decimal, okay, negative 0.954 ln of negative 0.954 minus 0.127 0.127i. Okay. So we will now evaluate the ln of this complex number. Again, convert this to polar form. So x is negative 0.954, y is negative 0.127. Therefore, what quadrant does the complex number lie? Both x and y are negative. Therefore, the complex number is in quadrant 3. So find the r. Formula, square root of x squared plus y squared. So square root, substitute x, negative 0.954 squared plus y, substitute negative 0.127 squared. And you can use your calculator. Square root of negative 0.954 square plus negative 0.127 squared, and it is approximately equal to 0.962. For theta, if the argument if the complex number is in quadrant 3, the formula for argument theta is arctan y over x minus pi, right? So substitute the value arctan of y, we have negative 0.127 divided by x, negative 0.954 minus pi. You can use your calculator. You have arctan of negative 0.127 divided by negative 0.954 minus pi. So your theta is approximately negative 3.009. Using your calculator, you can convert this directly to polar form. Just input negative 0.954 minus 0.127i. Then shift to 3. Okay. You got the same r, 0.962, and same theta, negative 3.009. Okay. Now, let's evaluate the ln of this complex number applying the formula. So, ln of this complex number is approximately equal to the ln of r, which is 0.962 plus I theta, which is negative 3.009. So, ln of 0.962 is approximately equal to negative 0.039, then minus 3.009i. So, this is the principal value for ln. Likewise, the principal value already for the arc coset of that's 2 plus 7i, right? Okay. Then, getting the general value. So the general value for this ln is, so copy the same real part, negative 0.039, plus copy the same theta, negative 3.009, but with added to pi n quantity times I. So this is the general value for n0 plus minus 1 plus minus 2 and so on. So this is the second set of answers. This is the general value and this is the principal value. Okay, let's check. Using your calculator, let's apply calculator techniques. So you will start with this expression. Okay. Input first the complex number inside the square root. So you have 2 plus 7i quantity squared minus 1. Okay, and then get the square root of the abs. So shift abs of the ans, angle of, so the argument shift to 1, argument of the ans. Then if we're trying to get first the principal square root, we must add 2 pi times 0, right? Then over 2. So we're just applying this formula. Equal. Okay, so this is the square root of this complex number. We need to add 1. So add the answer with 1. And then divide this numerator. This is now the value. Divide by 2 plus 7i. So divide by quantity, open parenthesis, 2 plus 7i, close parenthesis. Okay, so the expression inside the ln, the value is this one. Okay, the exact value. We're trying to get the ln now of this value. So just input ln of shift abs of the ans plus I argument. So shift to 1 ans. Then equal. Okay, let's check. So we got 0. Okay, I think we got, we don't have the same answer. Why? Okay, let's try again. Maybe I inputted something wrong. Because the calculator got a different answer. Let's try again, okay? So we will try to input first 2 plus 7i squared minus 1. Okay. Do we got negative 46? 2 plus 7i. I think we're incorrect. Negative 44 plus 28. So 4 minus 1 are coset. Sorry. Because in the formula, we copy it's plus 1, but here we copy minus 1. OMG. We're wrong. So let's check carelessness. I copied a wrong formula, or I wrote a wrong formula, although we have checked first, right? The formula supposed to be is not minus 1. It's not minus 1. It's plus 1. Okay? Right? It's plus 1. So are we wrong throughout the process? Let's check. So if this is 1, we will change this to plus. Sorry for the mistake. So plus 1, then 5 plus 1. Okay, we're still correct. I miscalculated. So if it is 1, supposed to be, if it's minus 1, supposed to be, I should have put 3 here, right? But luckily, I put 5. I computed 5. So we're lucky enough that we compensate for the mistake of the formula minus 1. We still be able to put 5 here in 4. Instead of 4 minus 1, the first in the first formula that I wrote, it should be 3, right? But luckily, I miscalculated 4 plus 1, 4 minus 1 as 5, which is still correct if you apply the formula, the correct formula, 4 plus 1. So it should be 5. And then 5 minus 49, negative 44. So still, our solutions are correct. Luckily, okay? So therefore, if you try to input this in your calculator, let's check. So we got the 2 plus 7i quantity squared plus 1. Okay. We still got negative 44 plus 28i. Now let's try the calculator technique. So square root of the the absolute value of the ans, then angle of the argument. So shift 2, 1, ans plus 2 pi times 0 over 2. Okay? And then we need to add 1, then divide the answer by 2 plus 7i, 2 plus 7i, and then get the ln of this expression. So ln of shift absolute value of the ans plus I shift to 1 ans. Okay, let's check. We should still get the correct answer, right? Okay. Approximately 0.038 minus 0.132i. So, correct. So, we're lucky enough, although at first, I wrote an incorrect formula because I originally put minus 1, right? I was lucky enough that I miscalculated here 4 minus 1 as 5 instead of 3, right? Because supposed to be, it should be 4 plus 1 using the correct formula, which is 5. So that's why we still got the same answer. Okay? So be careful with your formula. Okay? Don't commit the same mistakes that I did. So next, let's try to check whether our second set of answer is correct. Okay? So we will have the same expression. It's just that we will set k equal to 1. So start with this expression again. So input 2 plus 7i squared plus 1. Then square root of the ans shift abs of the ans. And angle of shift to 1 argument. But since this time, since we're considering k is equal to 1, we must add 2 pi times 1 in the de Moivre's formula over 2. Okay, and then again add 1, so plus 1, then divide 2 plus 7i, and then get the ln of this answer. So ln of shift abs of the ans plus I shift to 1 argument of the ans. Okay, checking the answer that we got for the second set of solution, it's approximately negative 0.039. We got negative 0.039, but in the calculator, it's negative 0.038. So it's just a discrepancy due to rounding off errors on every step of the solution, on every calculation. Then minus 3.009i. Okay. So we're approximately the same. Okay, now let's have the second problem. Or actually, if we continue, it's already the... So this is the fourth problem already. We have the fifth problem now. Okay, for the fifth problem, what if we got arc set of negative 6 plus I? Again, let's check the calculator. This time, be careful with the formula. Try not to mess up. Okay. For arc set z is equal to ln of 1 plus the square root of 1 minus z squared over z. Okay. It's clear. Formula for arc set of z is equal, okay, to ln of 1 plus the square root of 1 minus z squared over z. Okay. Wherein the value of z is equal to negative 6 plus I. So substituting that value of z, here we have arc set of z negative 6 plus I is equal to ln of 1 plus the square root of 1 minus z, which is negative 6 plus I squared over z negative 6 plus I. Okay. So simplify first the expression inside the square root. So 1 minus the quantity, square of a binomial again. So square negative 6, that's 36. Then product of the first and the second, negative 6 times I, negative 6i, times 2, negative 12i. Plus I squared, that will be I times I raised to the second power, that will be I squared, okay? Over negative 6 plus I. So we will have ln of 1 plus the square root of, so let's distribute this negative, 1 minus 36, so positive 12i, then minus I squared over negative 6 plus I. So ln of 1 plus the square root of, so 1 minus 36, you can combine that as negative 35, right? Okay, plus 12i, then minus I squared, that's negative 1. Therefore, negative of negative 1, it will become positive 1. Then over negative 6 plus I. So ln 1 plus, you can still combine negative 35 plus 1. Negative 34. Square root of negative 34 plus 12i. Okay. Divided by negative 6 plus I. Okay, so we will now evaluate the square root of negative 34 plus 12i. So convert again negative 34 plus 12i to polar form. So x is negative 34, y is 12, and it is in quadrant. Since x is negative and y is positive, quadrant 2. So the value of r, square root of x squared plus y squared, square root of x negative 34 square plus y 12 square. So you can use your calculator. Square root of negative 34 square plus 12 square. It is 10 square root of 13. Okay. Then for your theta, if the complex number is in quadrant 2, formula for theta is again arctan y over x plus pi. Substitute arctan of y 12 over x negative 34 plus pi. So arctan of 12 over negative 34 plus pi. Approximately 2.802 rad. So using calculator to convert negative 34 plus 12i to polar, input negative 34 plus 12i and then shift to 3. So you get the same r, 10 square root of 13, and same theta, 2.802. Applying the Moivre's theorem, therefore, square root of negative 34 plus 12i is now equal to the square root of r, 10 square root of 13, angle theta, which is 2.802 plus 2 pi k over again n, the invisible 2 here, over 2. Then this is for k, 0, and 1. So let's find first the value of the square root for k is equal to 0. So for k is equal to 0, therefore the square root of negative 34 plus 12i is square root of 10 square root of 13 angle 2.802 plus 2 pi k set to 0 over 2. So this is just 0. You don't need to write. So we just have square root of 10 square root of 13 angle 2.802 divided by 2 only, right? So that's 1.401. Okay. Then in polar trigonometric form, it's also equal to the square root of 10 square root of 13 cosine of 1.401 plus I sine of 1.401. And approximately, it's equal to, in rectangular form, input this in your calculator, square root of 10 square root of 13 angle of 1.401. Okay, so this is approximately equal to 3 decimal place, 1.015 plus 5.918i. Okay? You will plug in this principal value of the square root in the formula above this one. Let's copy. Okay. It is the formula for arc sech of negative 6 plus I, right? Okay, so substitute the value of this is square root, the principal square root. We got this one. So plus quantity 1.015 plus 5.918i over negative 6 plus I. And then you combine the real parts, 1 plus 1.015, that's 2.015 plus 5.918i over negative 6 plus I. So again, you can divide this manually, but it's harder because of the decimal. Instead, I will just use your calculator. So input 2.015 plus 5.918i over negative 6 plus I. So in decimal, it is approximately equal to negative 0.167 minus 1.014i. Okay. Now, evaluate this ln of complex number. Convert this to polar form. So, x is your negative 0.167. Your y is negative 1.014. So, both x and y are negative. Therefore, the complex number is in quadrant 3. R is square root of x squared plus y squared. So square root of x negative 0.167 square plus y is negative 1.014 square. Use your calculator. Square root of negative 0.167 square plus negative 1.014 square, approximately 1.028. Then for your theta, arctan of, if the complex number is in quadrant 3, the formula for theta is arctan y over x minus pi, right? Substitute the value, arctan of y, negative 1.014 over x, negative 0.167 minus pi. Input in your calculator, arctan of negative 1.014 over negative 0.167 minus 5. Approximately negative 1.734 rad. So using your calculator, to convert this directly to polar, just input negative 0.167 minus 1.014i. Okay? Then shift to 3. You will get the same R, 1.028, and same theta, negative 1.734. Therefore, the value of this ln, so the ln of this complex number is approximately equal, applying the formula, ln of R, 1.028 plus I theta, negative 1.734. So, ln of 1.028 is approximately equal to 0.028, then minus 1.734i. So this is the principal value of ln. Also, the principal value, final answer already, for the principal value of the arc sech. Arc sech of negative 6 plus I. We also find the general value of this ln. So it's the same, copy 0.028 plus negative 1.734, but with added 2 pi n, then quantity times I. This is the general value for n0 plus minus 1 plus minus 2 and so on. So this is the general value for the arc set of negative 6 plus I. Okay, but this is just the first set of answer because we must have 2 because of the square root, right? Let's consider now k is equal to 1 in the same formula for the square root of negative 34 plus 12i. So let's just copy the same formula. So we will get the next set of answers when we set k is equal to 1. Okay? So getting the square root of negative 34 plus 12i when k is equal to 1 is equal to the square root of 10, square root of 13, angle of 2.802 plus 2 pi k, which is now equal to 1, over same index 2. So you have square root of 10, square root of 13 angle. Input this in your calculator. So 2.802 plus 2 pi times 1, simply 2 pi over 2. We will get approximately 4.543. So in polar trigonometric form, it is equal to 10 square root of 13 cosine of 4.543 plus I sine of 4.543. In rectangular form, input this in your calculator. So square root of 10, square root of 13, angle of 4.543. So approximately negative 1.012 minus 5.919. Ay. Okay. And then substitute this second value of square root in the formula for arc set, this one. So it is now approximately equal to ln of 1 plus the second value of the square root of negative 34 plus 12 by this one, negative 1.012 minus 5.919i over negative 6 plus I. So simplify the numerator, combine the real parts. Okay, so what is 1 plus negative 1.012? Negative 0.012, right? Then copy minus 5.919i over negative 6 plus I. Again, you can solve it manually, but it's harder due to decimal places. Just use your calculator, divide negative 0.012 minus 5.919i divided by negative 6 plus I. And it is approximately equal to negative 0.158. So ln of negative 0.158 plus 0.960i. Okay, we try to get the ln of this complex number. So convert this to polar form. So x is negative 0.158, y is 0.960. So both x and not both. X is negative, y is positive. Therefore, the complex number is in quadrant 2. So r is the square root of x squared plus y squared. Square root of x, negative 0.158 square, plus y is 0.960 square. So using your calculator, square root of negative 0.158 158 square plus 0.960 square. It is 0.973 approximately. Then for your theta, it's arctan. If the complex number is in quadrant 2, formula for theta is arctan y over x plus pi. So arctan y, substitute 0.960 over x, substitute negative 0.158 plus pi. Use your calculator, arctan of 0.960 over negative 0.158 plus pi. Approximately 1.734, right? So check using your calculator. Convert this to polar form. Input negative 0.158 plus 0.960i. Then shift to 3. So the same value of r, 0.973, and same value for theta, 1.734 rad. If we now get the ln of this complex number, copy. Applying the formula, it is approximately equal to the ln of r that we got, 0.973, plus I theta, 1.734. So use your calculator, ln of 0.973, that's approximately negative 0.027, then plus 1.734 I. Okay, so this is the principal value of the ln. Likewise, the principal value already for the arc set itself, for the second set of answers. If we get the general value, okay, the general value of this ln is, just copy the real part, negative 0.027, plus copy the argument theta, 1.734, but with added 2 pi n times quantity I. So this is the general value. For n0, plus minus 1, plus minus 2, and so on. This is the general value for the second set of answer for the arc set. Arc set of negative 6 plus I. Okay, now let's check using calculator. So let's start with this expression. Okay, input the expression inside the square root. So 1 minus quantity negative 6 plus I, negative 6 plus I squared. This one. We got, okay, this time same, negative 34 plus 12i. Then we're trying to get the square root of this, negative 34 plus 12i. So input square root, shift abs of the ans, then angle of argument, shift to 1, argument of the ans. If we're getting first k is equal, or if we're setting first k is equal to 0 in the Moivre's theorem, we add 2 pi times 0, okay, over 2. So this is the principal square root, okay, then plus 1, then divide the ans by negative 6 plus I. So divide, open parenthesis, negative 6 plus I, close parenthesis. So this is now the value of the expression inside the ln, this one. Try to get the ln of this. So input ln of the absolute value of the ans plus I, shift to 1 ans. Let's check. Okay, we got approximately, okay, 0.027 in calcu. We got 0.028. So it's, the discrepancy is just due to the rounding off in every step of the solution. Minus 1.734i. So we got the same imaginary part up to 3 decimal place. So our answer is approximately the same. How about for the second answer? Again, let's start with this expression. So input again, 1 minus quantity negative 6 plus I squared. Okay. 1 minus quantity negative 6 plus I squared. Then get the square root of that. So square root of the abs of the ans. Then angle of fraction shift to 1, argument of the ans. This time, we're setting k is equal to 1. So we add 2 pi times 1, then over 2. So we will get the second square root of this expression, this 1. Then add 1, divide the numerator by negative 6 plus I. Okay, so this is now the value of the expression inside the ln. So we need to get the ln of this. Input ln of shift abs of the ans plus I shift to 1 argument of the ans. Then equal, let's check. Okay, the second set of answer, we got negative 0.027, correct, in 3 decimal place, plus 1.734i. So we're exactly the same answer, approximately up to 3 decimal place based on the calculator. Okay, next. So that's number 5. Okay, 6. Okay, for number 6, we got the last function, arcot. Okay. Arcot of negative 9 minus 4i. So what's the formula for arcot of z first? Okay, be careful again in writing down the formula. So let's check. Arcot of z is 1/2 ln of z plus 1 over z minus 1. Arcot of z is 1/2 ln of z plus 1 over z minus 1. Wherein the value of z is negative 9 minus 4i. So therefore, substitute that value of z, which is negative 9 minus 4i. In the formula, we have 1/2 ln of z, negative 9 minus 4i, plus 1 over z, negative 9 minus 4i minus 1. So 1/2 ln of negative 9 minus 4i plus 1, you can combine negative 9 plus 1. Okay, that's negative 8 minus 4i over negative 9 minus 1. Negative 10 minus 4i. Okay, notice we can factor out the numerator. We can factor out the 2 in the numerator. Okay. Or let's also include the negative. Factor out the negative 2 on the numerator. We have negative 2 times what? 4 minus plus 2i over, also we can factor out negative 2 in the denominator. We will have negative 2 times quantity 5 plus 2i. Okay. And we can cancel this negative 2. We will have 1/2 ln of 4 plus 2i over 5 plus 2i. Now we divide. This time it's easier to divide because we got whole numbers in the real and imaginary part of both numerator and denominator. So let's try to solve it manually this time. Although you can also input in your calculator. So we need to multiply both numerator and denominator of this complex number by the conjugate of the complex number in the denominator. So what's the conjugate of the denominator? 5 plus 2i. So copy the real part 5, then get the opposite sign of the imaginary part. So since we got positive 2i, its opposite side is negative 2i. So we need to copy this 5 minus 2i also in the denominator. So we multiply both numerator and denominator by the conjugate of 5 plus 2i, which is 5 minus 2i. So we will FOIL the numerator. 4 times 5, that's 20. 4 times negative 2i, negative 8i. 2i times 5, that's 10i. Then 2i times negative 2i, negative 4i squared. Over, so for the product of the denominators, if they are complex conjugate of each other, the shortcut formula is just the square of the real part, or the first term, 5. So you square that, you will have 5 square, plus the square of the imaginary part, or the coefficient of I, 2. Square of that will be 2 square. Or no need the parentheses. So simplifying the numerator, so 1 half ln of, so 20 negative 8i plus 10, positive 2i. Then minus 4i square is negative 1. Therefore, negative 4 times negative 1, it will be positive 4. Okay? Over 5 square, it's 25, plus 2 square, it's 4. So you have 1 half ln of 20 plus 4. Okay? That will be 24. Right? Then plus 2i over 25 plus 4. Or you can add 25 plus 4 now. That's 29. So you divide 24 by 29 and 2i by 29. You will have 1 half ln of 24 over 29 plus 2 over 29i. Okay, so this is the simplified answer in this division of complex number. So next step is to evaluate the ln of this complex number. So identify the x. Let's convert this first to polar. X is 24 over 29. Y is 2 over 29. So both x and y are positive. Therefore, the complex number is in quadrant 1. So r is the square root of x squared plus y squared. Square root of x is 24 over 29 square plus y is 2 over 29 square. You can use your calculator. Input the square root of 24 over 29 square plus the square of 2 over 29 approximately or exactly equal to 2 square root of 145 over 29. Okay. How about for the theta? If the complex number is in quadrant 1, formula for theta is arctan y over x, right? So arctan y, substitute 2 over 29 over x, 24 over 29. So it is equal to, so arctan of 2 over 29 over 24 over 29, it is approximately equal to 0.083 rad. Okay, now you can also check directly using your calculator. Convert this to polar. Just input 24 over 29 plus 2 over 29i. Then shift to 3. Okay, same r. 2 square root of 145 over 29 and same theta 0.083. Now, we will get the ln of this complex number, which is approximately equal. So the formula is ln of this r, 2 square root of 145 over 29 plus I theta, which is 0.083. Or that's ln of 2 square root of 145 over 29 plus 0.083i. Then, we still need to multiply by 1 half, right? Okay. So, multiply this by 1 half. Distribute. So, 1 half ln of 2 square root of 145 over 29 plus 0.083 over 2i. So, approximately, using your calculator, 1 half ln of 2 square root of 145 over 29, it is negative 0.093. Okay, the real part. For the imaginary, that's 0.083 over 2 or 0.042i. So this is the principal value of the ln. Likewise, the principal value of the arc cost. Arc cost of negative 9 minus 4i. Okay? How about the general value? So, for the general value, try to get the general value of the ln also. So, it is the same, this one. So, ln of 2 square root of 145 over 29 plus 0.083, but with added 2 pi n I. Okay? But we need to multiply it by 1 half also, right? In the formula, this one. So you distribute this 1 half. Excuse me. Sorry. So you will have 1 half ln of 2 square root of 145 over 29 plus 0.083 plus 2 pi n over 2i. So we already know the value of this. It's approximately this one, negative 0.093, right? And for this, you distribute this 2, divide 0.083 over 2 plus 2 pi n over 2 I. Okay, so you will have approximately negative 0.093 plus, you already know the value of 0.083 over 2. 0.042, right? So you got 0.042. Then plus, you cancel this 2. You will have pi n, right? Quantity times I. So this is the general value for n0 plus minus 1 plus minus 2 and so on. This is the general value for the arc cost of the complex number negative 9 minus 4i. Now let's check using our calculator. So you can start with this expression, input. Input first the expression inside the ln. So negative 9, minus 4i plus 1 over negative 9 minus 4i minus 1 equal. So see, we got the same answer. 24 over 29 plus 2 over 29i. And then get the ln of this answer. We will have ln of shift, absolute value of the ans, plus I, argument, so shift to 1 ans. And then we need to multiply by 1 half, right? So enclose this ln expression inside the parenthesis, open and close parenthesis. Okay? Then multiply this by 1 half equal. So, do we get the same answer? Approximately, okay, negative 0.093, 3 decimal place for the real part, plus 0.042i, okay, for the imaginary part. So, we're correct up to 3 decimal place based on the exact answer in the calculator. Okay, so I think that's it for this topic, inverse hyperbolic functions of complex numbers. So we already have solved problems on the 6 inverse hyperbolic functions, okay, for the first and the second part of this topic. Okay, so I hope you learned something from this video. So please subscribe to our YouTube channel if you haven't yet, and click the notification bell so that you will be updated whenever we have new uploaded videos or upcoming tutorials. Again, you can always watch the live streams for this series of topic all about advanced engineering mathematics subject. The links of the videos are in the description. Likewise, the main playlist for advanced engineering mathematics is also linked in the description. Okay, so see you on my next live, and God bless everyone. Take care always. Bye bye.